Okay, here we have the microcontroller for the Pixis Camera Field rotator. You'll see that I put it in a clear box. We have a small display here with some push buttons and a little display. This button here will run the Pixis clockwise, this one counterclockwise, and these two buttons will either increase or decrease the tracking rate that's displayed in the display. If I press the clockwise button, you can see the Pixis will begin to rotate, and if I push it the counterclockwise, it'll rotate in the other direction. It communicates with the Pixis via serial interface, which I've added a second serial interface up here to the controller. It has a primary serial interface down here, which is used for firmware upgrades, and also it'll print a series of documentation if you hook it up to a terminal on a PC or whatever. This is the power cable here. Now on this, when you first boot it up, what you will see, now we'll kill the power and it'll come up and scroll. Get that plug, there we go. It'll scroll through and show the name of the controller and some information. And it'll also tells you to press buttons 1 plus 3 for setup. So as soon as it's finished booting up, it looks for the Pixis, tells you it's found it or not, checks for a home position, then it goes into its default setting mode. Notice there's a small flashing LED light down there that tells us about the current status. That's a polling light. When it flashes red, that's stepping the motor. The camera video frame rate sometimes doesn't show the LED, but it's actually blinking continuously there as it drifts in and out of phase with the frame rate on the little camera. Anyway, if you press buttons 1 and 3 together, it'll enter the default setup mode. And first there's the default tracking rate, which is currently set at 360. You can change this to anything from lunar through sidereal and other ranges beyond that, in case there's an application for a comet or something like that you wanted to track with this for some reason. I tried to think of any possible future scenarios where you might want to use the rotators and add features to support those, even though I couldn't think of a purpose for them right now. It was easy to add to the firmware, so I just went ahead and did that. Anyway, you can change this by pressing up and down to change the defaults. And when you get to the settings you want, you press the continue key here. And this is motor speed correction, just in case you find at some point that there's a slight imperfections in the tracking rate due to motors. You can actually increase or decrease a correction factor here that will change the default for the motor. These settings here are saved to non-volatile memory, so they will survive a power cycle. So these are the cold boot configuration settings, so to speak. When we've got that set, we go to the next, default rotation direction. For our purposes, the correct rotation rate for the Heliostat is counterclockwise, but if something is changed or new equipment is added or the rotators are flipped over or some other variation is made, or maybe take it to the southern hemisphere, we may want to change the direction of rotation, and that setting here would allow us to do that. A motor holding current. This is a feature of stepper motors that they typically have what's called a holding current, so they can hold their position even when they're at a stationary position. The disadvantage, of course, of holding current is not only does it consume power, but it also generates heat. And of course, for astronomical purposes, extraneous stray heat is never considered a good thing. And so here we have the option to disable the holding current on the stepper motors for both the tabletop Heliostat as well as the Pixis. We set the off as the default. But if you find that for some reason those settings aren't sufficient for these devices to hold their position, you can enable holding currents, and it gives them a little more of a lock as they're sitting in their position between steps. This setting here is the button timeout. This is a safety feature. I have it set by default to 12 hours, but you can run this down from 0 to 24 hours. If you set it to 0, it disables this feature, which means this thing will rotate continuously. If you leave it at some default like 12 hours, it will rotate for a period of 12 hours, and then it will enter a pause mode, and the display will display paused, and basically it'll stop until some button is pressed. And the button timeout is, of course, the number of hours from the last button press before it stops the motors. This is designed to prevent wrap-up of cables on cameras or from things being impacted potentially by cameras or instruments and so forth. I couldn't think of a good application for it right now, but maybe something in the future might require this feature. So it was easy to add now, so I've done that. Once I've set the hours I want, I can go ahead and press the next key over here to go to the next step of the configuration. I've also added the feature that if you completely screw up the settings and wish to go back to the original programmatic defaults, you can do that here. Yes or no. If you say yes, it will reset all the default settings to the original program defaults rather than the power-up defaults that you can set yourself. Once you've pressed that, as the settings complete, then it'll go back to run mode, and you notice that stepping right here, it's catching up from where it was being suspended while you're in the configuration mode. So it's done the number of steps needed to catch up to where it left off. So it is possible to go into the configuration mode while you're tracking the sun, make changes, and when you get out, the rotator will catch up. Now this is also this is a little harder to display, but this is what am I looking for? This is a logic probe, an 8-channel logic probe, and this shows us the stepper motor pulses, the controls over here, which are the input to the control electronics, and this is the output that's actually going to the motors here. And this is part of what I use to design the circuit and optimize it for stepping motor controls. The other controller is almost identical. This is the one that runs the tabletop rotator. The display looks a little bit different, but other than that, it's basically the same device. And what it does is you also can rotate here. I've got the motor for the tabletop rotator sitting here, and as I press these buttons, the clockwise and counterclockwise, you can see it'll go through its different modes there, and you can see it running. This one I've designed a little bit differently. When you first press the button, the motor will start out slow, then it moves into a maximum speed. This allows you to do small corrections, but at the same time you can hold it down and go to larger corrections to change the orientation of the table in the drawing to the sun or the moon or whatever else you have the heliostat pointed at. It also has the flashing light, it has the same menu settings, everything is pretty much identical, has holding current options. Biggest difference is this controller here with the electronics up in here, that it drives the stepper motor directly, where the other controller is designed to talk out the serial interface back here, where it then talks to the serial interface of the Pixis rotator to allow us to drive it at sidereal rate, which is a feature that the Pixis normally cannot do. There's been no modifications to the Pixis rotator, so we of course can easily take this thing, hook up the factory serial to USB cable, and power up my PC as originally intended. You can move back and forth just by simply changing this cable right here to what device you got it connected to. Well, that's sort of it. That's just a quick tour of the microcontrollers. This right here is the programming cable that I've got plugged on here right now that allows me to do firmware upgrades and changes. Both of them have a program port, and that's it.